We're beginning this section on section 2.3, continuous functions. We're going to start with a couple of prior assumptions. The first assumption in the study of mathematics was that all functions were continuous. It was assumed that many things that occurred naturally operated on a continuum without start, without end, kind of like an ocean wave. But then it was discovered that light is emitted in particles, which means not all functions were continuous, and the prior assumption was incorrect. Now let's look at a situation for endpoints. Look at endpoint A. Endpoint A can only be approached from the left side, from the right side. So if you're looking at a left side endpoint, this is going to be continuous. Is if you're approaching A from the right side, if that limit is actually equal to the value of the function, as in there are no open holes there, it must be closed at A, then it's continuous. So if this is true, continuous at A. Let's look at the other side for B. If the limit as x approaches B from the left, which is the only way you can get to it, if that is equal to the actual function value, no open holes, then it's continuous at x is equal to B. Now if we look at this piecewise function, you can see areas where this graph is disconnected, or it has holes in it. If you look at this endpoint on the very end, right here, there is a hole in that. X may be approaching 2, but x can never be 2. It's not continuous. If you look right here, where x is approaching 0, there's no limit there because the right side limit is 2, and actually the left side limit is 2, and the right side limit is 0. So the limit doesn't exist, but look at it. It's also disconnected, so it's not continuous. Look at this one. As x approaches 2, there is a closed hole, and whether you approach it from the left or the right, you can get to the point. There's only a single value when x is approaching 2, and that's -2. So it is continuous at that point. In order to draw this graph, I would have to put my pen down here, draw along the graph, lift up. And then I'd have to come down here, draw my graph, but I could keep on going in order to draw the rest of the graph. That portion of the graph is continuous, but we're looking at individual points right now. So let's say that this is an interior point, C. Our function rule, the theorem says about continuous points, is that if the limit as x approaches C of our function is equal to the value of the function at C, then f of x is a continuous function. This is for interior points on an interval. C is on an interior, it's not an endpoint. Okay, let's put this into action. Let's look at the function f of x is equal to 2x plus 3. The question is, where is it continuous? We could look at the graph, but I'd like to try it algebraically. Underneath the radical, right here, 2x plus 3 must be positive or equal to 0. Cannot be negative, or we would have imaginary numbers. This is just like finding the domain of a function. So we're going to take the 2x plus 3, and since it must be greater than or equal to 0, we're just going to set up an inequality and solve it. So then x has to be greater than or equal to negative 3 over 2. It's continuous on this function. There are no holes in this function. And if we look at the graph, if you graph it, let's say this is negative 3 over 2, this graph looks something like this. So if you look on the other side, less than negative 3/2, there's no graph there. So it's discontinuous where there's no graph, where it cannot be graphed. So discontinuous where x is less than negative 3 over 2. There are three types of discontinuity. The first one is removable. With removable, this can be factored out of a function. And what it looks like is a hole in the graph. It's very tiny, and you would have to zoom in on the area where the hole is in the graph very, very tightly. I'll show you an example of this in a minute. Second kind is jump. There is a physical gap in the graph, as is shown in a piecewise function. And the third kind is infinite. And this is the type that we see the most often, and it has the presence of a vertical asymptote. Example time. So we're going to examine this function. We can look at it graphically, but we're going to look at it algebraically. And I can see that this function can be factored. So we're going to factor the denominator. And we're going to have two values of x that would make my denominator 0. So we are not continuous where x is negative 1 and where x is 1. The question now is to ask, what type of discontinuity is it? Now let's look at x plus 1. We can factor that out. So if we can factor it out, that means that at negative 1, it's removable. There is a hole in the graph. But that means that at x is equal to 1 is a vertical asymptote, which means it's an infinite discontinuity. And that is the lesson on continuous functions.